Okay, so in order to download AMPL ID, you can go to the course site, and in the topic 4, you have you can download the zip file here. But this is for Windows. If you want to if you want to download other version, or if you want to download the demo from AMPL website, you can just Google AMPL demo. The first choice is the website you want to visit, and for Windows here you have two options: the 32-bit version or 64-bit version. As for the Linux and the Mac OS, you can just follow the guideline here. And after you download the zip file, you can extract it. It will give you a folder, which is this one. And you click in the AMPL ID, and then you see you can see this application, and just double click it, and it will come as this one. So for the AMPL, it has 3 files. By the way, when you click this one, you can create a new file here. So it will have except the text file, you have 3 options, 3 file extension. The first one is for the model file. The second one is for the data file. The third one is for the command file. So basically, what you first want to do is you start with a model file. I already have one here. So so it's like so this is place where you write all your model. So for example, usually how we started this one is that we create a set for the index. For example, if I have 9 variable, x1, x2, x3, all the way up to x9, let's say I create an index set. Let's say I'll call this S. So we first look at this part. Let's call this set X. I'll say S is from 1 to N, and I'm stating N equals to 9 here. You can just say this is 9, so you do not need say N. But a more convenient but more usual way is to put the end of the index as some letter, and define the letter at the very beginning. And here I'm also setting, like I'm also giving another set for the index. So I think many of you already know AMPL a little bit. So if you have other conventions that are different from I'm showing you here, you can always say it is probably better way. There's some better way to do this or do that. I learn AMPL by myself, so my ways may not always be the best approach. So after you define the set for the indices, for the variables, okay, for variables and parameters, and now you can let's define some parameters. So parameter means is that they are the data part of the model. They are the coefficients of the model, of the inequalities, for example. So for example, like people always say we have lower bounds, we have upper bounds for the variables. What you can do is you can write the lower bound upper bound in this way. So I'm calling this one and first claim that this is a parameter. Like I'm claiming here is a set. Say I call this LB as for the lower bound. I say it will be indexed by the what numbers, the numbers in the set S, and I put a semicolon here. I'll say that is the first statement. So remember, always put a semicolon at the end. And this is equivalent, meaning this one. So okay, and I'm for the in a similar fashion, I'm putting an upper bound here. You can also different parameter in this way. So let me make this wider. You can also define a parameter in this way. So for example, if I have some parameter I'm calling the first parameter, it will be indexed by the indices from 1 to 100. So I'm calling this index set t. And I also have a second parameter, but the second parameter will be entirely based on the first parameter. Like if it's following this formula. For example, so for every element in the second parameter, what will be the first parameter divided with the same index divided by 2 and plus 3. If there's such a relation between two parameters, I can just write I can just define the second parameter in this way. So this is so the curly bracket here means that for all elements I'm giving this name I for all elements in the set T, it will be equal to this one. And you can see I'm not giving value for the parameter lower bounds, upper bounds. You can give value here in the mode file, and like I'm doing here, like I'm doing the first line. You can also give the data in the data file. It's like for example, you want to use the same model file for different data. You would better to put data in the data file. But if you just have one data for one model, you can just put data inside the model file. So that's about the parameter. After we have all the coefficients, all the parameters, we can define variables. For in the most simple case, if I want to define variable as denote variable as x, and I want to index x from 1 to 9, so I put the set curly brackets s here for represent the index. This is the most simple, the most straightforward one. But if I want to say those x has some lower bound and upper bound, I can define those lower bounds and upper bound in the constraint later. But I can also define the here when I claim the variable x here. So which is, as you can see here, it is greater than for all I in the index set s, xi is greater than or equal to the lower bound with index I is, and it's less than or equal to the upper bound with with the index I. So this is equivalent to so this statement is equivalent to this statement. And if you know the lower bound is 0, you can just put it's greater than 0 here. And if you know the variable is binary, you can just say it's binary. Okay. Yeah. So I think that's how you define variables. And as for if you want to next if we can go to say go to the objective function. So it's like if you want to minimize, you just have minimize. If you want to maximize, you just have maximize. So in a standard way, I want to minimize. Say let's say I want to minimize the summation of all possible x. So I want to minimize sum. And I'm using clean bar. So for all I in set s, or summation of all I in set s, xi. So for example, here I'm just use semicolon to end this statement. So which means that in this mode, I want to minimize the summation of all x. And I'm importing constraint. So subject to, oh, sorry, one thing, always give a name to the to this expression. So I'm calling this obj, or you can have like some other name, for example. I'll give a name here. Give a name to refer to this objective function, and also give a name to refer to a constraint. Say I'm saying constraint 1. Like something complicated. For all I in 1 to -1, xi minus xi plus 1 greater than or equal to 2, for example. Let's say we have the let's first do not define lower bounds and upper bounds here, those things. And if you just have just want to put all the data in the model file, you actually do not need the command file. You don't need the .run file. You can just in that type solve. Or you can also choose the you can say I'm choosing solver Cplex and I want to solve. By the way, the AMPL IDE has some very bad features that it will not save automatically. So always manually save your file. Otherwise, if you do not save your file and you close the IDE, all your work is wasted. Okay, that's very important one. And so here, I think it shall run. So in order to run this, model, type in include, and the name of the file with the extension and semicolon. Yes, it works. So it calls Cplex, but you can see it does not show any optimizer that show anything. So in order to print out the optimizer, in order to print out the objective value, you type display. So it's like print in the Python or printf in the MATLAB. So remember we gave name to those expressions, right? So you can type it. You want to see the objective value, say display some the name. You want to see the variable, you say display x, and save your file. And but in this case, it's like in this console, the AMPL will already remember that you already define n, you already define s. Those things. If you run the command again, you will see it will say this the n is already defined. So you can just say reset. Of course, you can always put the reset at the beginning of the model, but I'm not really suggest you to do that. If you have a data file, if you have a .run files, I will show where you should put reset later in another example. But if you just have one model file, you can put reset here. So for now, I'm not doing that. After I do the reset, it clear all the memories, and then I include this model file, and then run this file. You can see say sound of name is 0. It has say all x should be 0. It's true, right? Because we are just summarizing those things, but it's kind of like well, it's a very boring problem. So let me say some lower bound, upper bound. So if I want to define some lower bound, I'm saying each lower bound is 0. 0 is a 1. or more interested, each lower bound is I. Let's say each upper bound is I square. And say L greater than or equal. Okay. Let's say reset, run the model. Oh, it's still 0. Oh, I'm sorry. It's it's invisible. Let me do the try. Okay. Okay, good. So so this is a physical problem. As you can see, all x is exactly equal to the lower bound, and the minimized objective value is 45. The other thing is that so there are some other techniques for the display. You can like display the very specific things, but if you say you have many variables, you have many constraints, you want to see all those constraints, you want to see all those variables values, what you can do alternatively is display use this command, display coname con dot slack display where is it? I think that's the correct. Let's see. Good. Okay, so what I'm doing here is that those things start with the underline. They are the reference, very in general in the in AMPL, regardless what's the name of the variable, the name of the expression you give. So so no matter how I change this name, change some random name here, I'm changing this constraint name to some other random name. It will still show you it will still refer to the correct thing you want, because by claiming the correct type of things you are initialized, you are right. The AMPL knows this is constraint, and the AMPL knows this is variable, the AMPL knows this is objective function. So so regardless of what name you give those expressions, you can just use this kind of like those underline things to show that what you are looking for. This is the objective value. This is the constraint name. This is the slack variable value corresponding to each constraint. And then this is the variable name. This is the variable value. And later you will see in NEOS, if you want to display, you want to print objective value, if you want to print the variable value, you have to do those things. You cannot display some specific name, because the variable names in the NEOS will be like I think they will give just their own name for the variables for those things. So you have to use command like that. So this is the concrete example for AMPL. If we do not want to put any data in the model file, the example is here. So so it's generally which is very similar to the one before. I'm giving those two parameters that define the maximum value of the index set. It's very standard ABC, and A is the matrix. And we only have one variable x, and we want to minimize the dot product between vector C and the variable, and we are constraining this ax equal to b. and this is very standard x greater than or equal to 0. So this is the standard model, and then I can put all the data in this dot data file. So in the first line, you always say it's data. You also put this one, regardless what kind of file what kind of model you are using, and notice that instead of like the one shot, I only use equal sign here. You see, you can see we have a colon sign here. So that's the difference in terms of the format. So always use this symbol to define the values in the dot data file, but not in the model file. Okay. And then so for all the parameter we have, we define the value for the mn. We define 2, 3. For C is a vector of parameters, and it's indexed by J, so it will index from 1 to 3, because we define n equal to 3 here. So you just write C in this format. So 1 represents the index 1 corresponding to 12, index 2 corresponding to 6. So C1 is 12, C2 is 6. Those things similar for B, and for A. For A is a matrix, so yeah. So those 1, 2, 3, and those 1, 2 are represent index. So for A11 is 8, A12 is 6. Those things. And in terms of the MATLAB, that's how you write A. I think that should be clear. Okay, and let's see the ROM file. So basically, if you have this model file, data file, ROM file, so always put a reset to clear the memory, and you say this ROM file is corresponding to this model file, and this ROM file is corresponding to this data file. And then you choose server to be simplex. You can you have so in the AMPL IDE, you see all those server names. So that's all the server along come with the demo version of the AMPL IDE. It has Groovy, right? Yeah, it has Groovy. Yeah. So for example, if I want to choose Groovy, let's say that's for C++, and you can set the detail option for each solver. For example, you want the Groovy use LP method. I forgot which. I think it's integral point. Let's see. So one question is that how do we know what options of each solver have? I think say you can just Google the AMPL Groovy options. You have the documentation. It show you that so LP. Is this I or L? Yes. What does it? Anyway, you can try the document later. Okay. And this is how you import the. Oh, by the way. C plus options. By the way, this is how you, if you want to import multiple options for the solver, you can follow this format. You can just have use space between different options and assign value for the options with equal sign here, and put this punctuation. Okay. And again, tap solve. And I'm here using just the common, the universal name to represent the objective function variable. And if you want to save your output results to some txt file, you can use this little. So the single arrow represent it's creating. You are creating this. You are creating a file called output.txt, and you input what you have in the from the display obj to this file, and the double arrow means that so what you have from this statement will be appended to this file, so it will not overwrite what you have already. Okay. So let's see, and in the command line you have include you only include this .run file. So problem one run.run. Yeah. So that's all you have, and in the txt, you have exactly the same thing. Okay. Okay. Don't say. So I think that. By the way, you also have this slides in the on the course site, which is located here. I think it's basically just what I was saying. And if you are interested in this, a more complicated transportation example, it is here. I think it's basically it's very similar to what I have already shown you. So yeah. Oh, by the way, another interesting thing is that for stat, you do not always need to use numbers. Okay, in this model, you can just say you can say you do not need to define the stat in the model file, and if you can use some other name, you can use characters to define the index, and always put a space between each element. And in this way, you can define the parameter. So it has 3 parameters. So it has parameter like the cost, which is indexed by food. fmin is indexed by food. Those things. And you can assign the value for the parameter in this way. So so for each index, it has cost. This value, it has fmin. This value, it has fmax. This value. So instead of define fmax in one line, you can define those 3 variables index by index in this format. Okay. So when you write your own code, you just you can use my example here and delete the corresponding entries and type your own things, own data. Okay. I think that's about all the things I have for the AMPL. From the problem I have seen for the second assignment, I would say that will be enough, or even the assignment after the second assignment. I don't. So the next thing is that and in the second assignment, I think you will also want to initialize. I want to minimize some function with some starting point. So I'm randomly creating. So I randomly created this function, and I want to minimize this function with this starting point. So what we have is that we define the parameter which means the maximize the index, and we define the stat here. I also define another stat for up to n over 2 because it's a corresponding to a summation here. And the variable is x. So I would say basically I just import what I see here to here. So if you have any question why I can import in this way, ask me now, okay? I think it's kind of very obvious. And then I say, then I initialize, and then I provide the initial point in this format. So use let to say this is the initial point that I want some solver to search, and the index is start from 1. So all the index will have value 0.5. The even index will have value 2. So all the even index I'm setting the value to be 2. The all the index I'm setting the value to be 0.5. By the way, notice that although I'm saying that in the model file to assign the value for the parameters, you just use equal sign. But here with let, we have to use this colon plus equal sign. Okay. And then we have the model file. And then I say I want to minimize this model on NEOS server. So in order to access NEOS server, I have a link here. So just copy this. The first thing I suggest you to do is you set up an account, because because by doing this, all the jobs that submitted to NEOS server will be saved under your account, and you can access those things anytime. Otherwise, you have to always remember the job number and the random password generated for the job, which is very time consuming. Okay, so I already have an account, so let's skip the registration process, and then you click submit a job to NEOS. So you can choose solver. So NEOS is a solver that with all the solvers already implemented on in the NEOS in the solver. You can choose the problem type. You can choose the solver based on problem type. For example, the problem here is nonlinear. It's probably non-convex. It's some random function that just commutes the mathematical operations here. So maybe you want to choose some solver for the global optimization, like things here. For example, like piece one. By the way, piece one is made by one of our professors at Lehigh SC. And you can see all those solvers like Symphony. You probably it's another software made by Professor Zat Lihai. And if you already know what software you can use, you can also search through the alphabet. For example, I want to use this software, and to say, and it says it can accept the file, the model program under the AMPL. So I click in. So it basically has three elements. The place to submit the model file, the place submit to data file, and the command file. So it's like if you have data inside the model file, you can just submit the model file. But if you have some data, you can submit. But in this example, we do not have data file. You do not really need to submit the command file, but I will stress you to do that. And like I mentioned that in the NEOS, you cannot display X, you cannot display OBJ. You have to use something like here. But like let's say and in the second assignment, what you will see, you will also want to record the number of iterations, those things. So what I'm having here is that I'm saying save all the subsequent commands after these commands to a file called output.txt. Okay, so let's see what I will do. So by the way, this command file, I'm naming this neos.run. Is that this file can be used for all the models submitted to the NEOS server. Okay. Yeah. And because it's a small file, I'm clicking this setting short priority so it can deal with the job quicker. And then typing email because it will send all the results to my email address. And you can see, if you do not register account, you need to remember the information here, your job number and the password generated. Okay. And it should be very quick. Okay, yeah. You see it has OBJ, objective value. It has it does not have constraints, so it print nothing. And you can see the variable value here. And because I'm saying I want the NEOS server to save all the subsequent outputs to this file, I'm having this extra zip file. So download this one. Which is, and you can see it has a output.txt, which is just corresponding to the name here. You can see it's full variable. You can see it exactly saves all the printing out starting from here to here. That right? Okay. So it records the number of iteration, the number of function evaluations, the objective value, and all the printout you want. Also, because I sign in my account, you can access the same job. You can access page from your account and also from your email. Yeah, which is exactly the same thing in this page. Okay. Oh, by the way, yeah. So because I made this function up, I actually do not know what's this function. What is the true minimum of this function? So I also write the MATLAB file to solve. I think you probably also need to use some new solvers from MATLAB. So I also made an example of the usage of those 3 new solvers. It's slow. Okay. Yeah. So so it's like so I'm use the first solver is GA, the genetic algorithm. The second solver is the simulated annealing, and this one. All those things are format printing. You can just ignore it. But that's easier to see the results. Click run. That's the starting point. You can see the format printing here. The minimum is indeed 162, which is the same value as what we have in the from the news. But all 3 solvers gives different minimizer. Okay. Oh, by the way, I think last time my MATLAB intro is quite bad, or was quite bad. So if you have some questions about the MATLAB, or if you want me to start from the beginning, like how to write for loop in the MATLAB, how to do some plots in the MATLAB, you can email me, and we can set up another time for a more more detailed intro for the MATLAB. Okay, that's about all the things I want to show you. Do you have any questions? If not, we stop the recording.